It is the middle of July. Your refrigerator compressor is humming non-stop, but inside, your food is barely cool. Before you call a repair technician, there are 4 physical adjustments you can make to your kitchen right now. These steps will lower your electricity bill, give your compressor a necessary break, and restore the machine's cooling capacity. To understand why your fridge is struggling, we need to look at the basic physics of how it operates. The core rule of thermodynamics is simple. Heat energy always flows from a hot source to a colder destination. If you mix hot and cold water, the thermal energy from the hot water transfers directly into the cold water. The larger the temperature gap between the two, the faster that heat transfer happens. Let's look at this diagram showing how your fridge breathes. In the winter, your kitchen is relatively cool. The condenser coil on the back of your fridge gets hot as it runs. Because of the large temperature difference between the hot coil and the cool room, the heat from the fridge flows effortlessly out into the surrounding air. But in the summer, that dynamic changes. The ambient temperature of your kitchen rises. Now you have a hot condenser coil sitting in a hot room. Without a clear, colder destination, the heat struggles to dissipate. To force the heat transfer to occur, the refrigerator runs its compressor longer to make its coils significantly hotter than the surrounding room. It works overtime just to dump its exhaust heat. Summer-proofing a fridge requires physically assisting the machine as it expels its extreme exhaust heat. Step 1 is locating exactly where your unit expels its heat. Place your hands on the exterior side panels and the back of the refrigerator. You might expect to find an exposed metal grid on the back. While older models have these rear coils, many modern refrigerators conceal the condenser coils directly inside the side walls. If those side panels feel warm to the touch, you have found your heat zones. Once you locate the heat source, pull the appliance out to leave a 3 to 4 inch gap between the unit, the back wall, and cabinetry. This gap creates a necessary physical buffer. It allows the natural air currents in your kitchen to flow over the warm panels and sweep the stagnant exhaust heat away from the coils. Pushing a refrigerator flush against a wall prevents this airflow. The machine ends up trapped in an envelope of its own exhaust, which neutralizes the internal cooling process entirely. Step 2 moves us from the exterior exhaust to the interior cold air distribution system. Your fridge relies on internal fans to blow cold air currents across your food. If those currents do not have physical pathways to travel through, the items in the center stay warm. Look at this split screen comparison. A jam-packed interior blocks the fan's output. To cool efficiently, the layout needs clear vertical and horizontal gaps between containers. Pay special attention to the vents located on the back wall of the interior. Pushing tall boxes or large leftovers directly against these vents cuts off the primary cold air supply for the entire compartment. Step 3 requires changing how we interact with the appliance. We need to adopt a quick close rule. This means stopping the habit of opening the door and standing in front of it while deciding what to eat. This diagram shows the rapid thermal exchange happening the moment you pull the handle. Because cold air is heavy and dense, it spills out onto your kitchen floor. Simultaneously, warm room air rushes in to fill the vacuum at the top shelves. Combining a tightly packed interior with prolonged door openings clears out whatever chilled air managed to circulate. The compressor then has to perform double the mechanical workload just to reclaim its baseline temperature. Step 4 involves your internal temperature dial or digital thermostat. When the kitchen gets hot, the immediate reaction for most people is to crank that setting all the way up to maximum. A thermostat does not increase the strength or the speed of the cold air. It only tells the compressor what target temperature to hit before it is allowed to turn off. This graph illustrates the problem. The bottom line represents a normal target temperature. The machine reaches it, and the compressor powers down to rest. The top line represents the maximum setting. In a hot room, the fridge physically cannot reach that extreme low temperature. Because it never hits the target, the compressor never gets the signal to stop. It runs infinitely, consuming massive amounts of electricity with zero additional cooling benefit. Dialing the thermostat down to a normal setting aligns the machine's workload with the physical limits of a hot room. It allows the compressor to finally cycle off. By restoring the exterior exhaust space, clearing the internal airways, and correcting the thermostat trap, you remove the mechanical roadblocks hindering your appliance. Within 24 hours of completing this audit, you will hear a distinct change. The compressor will successfully cycle off and rest. Your appliance will return to maintaining a consistent, protected internal climate. Every refrigerator has an operational ceiling tied to the ambient temperature around it. Accepting that baseline limit is necessary to keep the unit running efficiently. Maintaining a cold interior during extreme heat relies on organizing your kitchen to facilitate the natural physics of heat transfer.